So, welcome. I'm the chair of the Department of Mathematics. It's my pleasure to welcome you for this lecture about mathematics and juggling. It's also my pleasure to introduce Allen Knutson, who is going to give this talk. He obtained his PhD at MIT in 1996. He then went on the West Coast in California, but finally he wanted to see some winter, so he came back here. So he's going to talk about mathematics and juggling. I have some worried about the juggling part. I've studied his CV, so I can assure you that he knows how to prove theorems. If I was invited to a talk about the structure of French gastronomy by a mathematician, I would be very worried of testing the cuisine. So I'm curious to see about the juggling. I also thought about something about the analogy between juggling and mathematics. If you learn 1 dimension, 2 dimension, 3 dimension, then it's really very easy to go to 4, 5, 6, an infinite dimension. If you juggle 2 balls, you juggle 3 balls, doesn't help so much, I think, with juggling more. And 6, 7, that's a lot of balls, I understand. So anyway, Alan, that's your turn.
All right, well, thanks for coming and seeing me here instead of being out enjoying this beautiful spring day. So why should there be a mathematics of juggling? It's a little loud, huh? I don't need to convince this audience about this. I mean, there should be mathematics of anything. Anything that's sufficiently well understood should be the mathematics of that thing. And juggling is particularly mathematizable, as I'll show you in a minute. So I think of this as an applied mathematics talk. I want to tell you a nice numbering system for juggling patterns that's good for recording patterns. And when it was invented in 1985, it wasn't as easy to transmit video clips around the net as it is today. So it was much nicer to have a nice pithy numerical way of talking about juggling patterns when you wanted to talk to people about on rec.juggling on Usenet. So it's good for recording patterns. It's good for creating new patterns from old ones. And that's true if you have a difficult pattern you'd like to learn and you'd like to come up with something slightly simpler. And then that's still too hard, so something slightly simpler, and that's still too hard. And at least find a bunch of stepping stones. Or what's usually what jugglers want to do is to find something harder. You know, the jugglers are not efficiency experts. The question is always, there's got to be a harder way to do this. So I'll show you some of that. So before I make things numerical, let me give you the following idea of how you might draw a juggling pattern so that you have a picture of it instead of a video. Imagine we have, where the lights don't work, a camera mounted in the ceiling that's looking down at my juggling these 3 glowing balls, and we're going to take a long exposure photograph. What would that look like? So it's only seeing any particular ball move from side to side. It doesn't see the up and down. And so from side to side, any particular ball is going to be looking like it's doing this. That. Okay, so I have these 3 balls, one that's doing that, one that's doing that, and one like that. Okay? Is this visible, or am I going to have to draw thicker? Visible? Okay. So what's going on here? This is my left hand. This is my right hand. This direction is time. And so at any particular time, if we stop the juggler and take a flash photograph, what we'll see is these 3 balls. And okay, so this is a pattern of what's called the 3-ball cascades that I was just doing, the standard pattern of 3 balls. Let me just make sure you know the structure of the 3-ball cascade. So it's this, the usual pattern of 3 balls. It's much, much easier than this one, which we'll discuss a little later. See how much slower and lower it is. because I'm not putting all the work on one hand. Any particular ball here is getting thrown from the middle to the outside, and then caught and brought back in and thrown from the middle to the outside. And I can give you tips about learning actually to juggle. Most of it is waiting. You come here and you wait. Oh, gotta throw. Oh, okay, I'll wait. So most of the time, I'm sitting here waiting, and I'm always throwing from the middle to the outside in this figure 8 pattern. Actually, in Spanish, this pattern is not called the cascade, it's called el ocho. And this is el ocho con tres, which I think is so the 8 with 3. Because of the figure 8 pattern that any particular ball is doing. All right, let's do a more complicated one. In the middle of doing 3, I'm going to do 2 throws. So all these throws were crossing from one hand to the other. They're all crossing throws. I'm going to do 2 throws like this that do not cross. And they'll have a little bit of time underneath that I used here to clap. And in that time underneath, I'll hand the other ball straight across. So let's try and get that so the colors are right. Well, I didn't. Okay, but there's going to be up, up, and across. And the ones that go up are not crossing. There's ways you could vary that. One could do it and not do any of the ordinary throws. But let's just stick with this up, up, and across. What does that look like to the camera in the ceiling? So we've got a couple of standard throws, let's say. And then this one doesn't go from the right hand to the left hand, it goes back. Whoops, up. 1, 2, these were 5s, not 3s, sorry. There. Okay, this one doesn't go from the right hand to the left hand, it goes from the right hand back to the right hand. So that would really go straight on here, but I'm going to draw it out here so I don't get confused. So it doesn't collide with that, even on the picture. Hopefully not in the air either. And this one is good. So that was from my right hand, back to my right hand, then from my left hand, back to my left hand. And then there's this one, which is the one straight across. So notice this slope is much higher than that slope. It's covering more space in less time. That ball going across is going very fast. And then I go back to these ordinary throws that one would ordinarily do in 3, in the 3-ball cascade. Okay, so that's that trick I was doing a moment ago, just once in the middle of 3. Okay. So this, you could imagine drawing pictures like this and shuttling them around the net in order to convey what pattern you want to be talking about. But we can actually compress this a whole lot too if we don't keep track of, all this picture. I just want to keep track of the basic thing. So here's the idea of, and I'll explain the name later, these juggling patterns. This notation is called Siteswap, so I'll tell you why later. Record only the order that balls are thrown and caught. So let me show you a couple of patterns that are different as juggling patterns, but are the same if all you're keeping track of is the order. So here was 3 that I was doing before, that we have pictured up there. And here's also 3, but now all these throws are from the outside to the inside. So sometimes called the reverse cascade. Or I could do it reverse in one hand and not in the other. And none of these are different in terms of the order that balls are thrown and caught. Here's another one that has the same order that balls are thrown and caught, I hope you see. But people would often call this a different pattern. So this one is actually, that one actually has a name. It's named after Steve Mills. It's called Mills' Mess. So that's what we're going to keep track of, and I'll say that numerically here. So what I'm going to keep track of, whenever I do a throw, so a throw number, or let me say an end throw, means that after it's thrown, n minus 1 other throws happen. Then it lands. Okay, so here I do this throw, and while it's in the air, I throw my other 2 balls. And then it's the third one to land. So that's a 3. And in fact, all these are 3s. So this pattern, not too surprising, you might call it 3, 3, 3, 3, 3. Okay. So what's different here? 3, 3, 3. This guy, while it's in the air, I do 1, 2, 3 other things, and then it's the fourth to land. 4, 4. This guy, I throw it, and it's the very next thing. Nothing else happens in between. That's a 1. And then I go back to 3s. So this is what jugglers actually say aloud to one another at juggling conventions. Oh yeah, so in the middle of that you do 4, 4, 1, and you go back to 3s. Or you just run 4, 4, 1 for a while. So I was showing you that before when I was doing 3, 3, 3, 4, 4, 1, 4, 4, 1, 3, 3, 3, 3, 4, 4, 1, 4, 4, 1, 4, 4, 1, 4, 4, 1, 3, 3, 3, 3, 3, 3, 3. So another slight variation, 4, 4, 1, 3, 4, 4, 1, 3, 4, 4, 1, 3, 4, 4, 1, 3. So in this one, the green ball is only doing 1s and 3s. The red and silver are only doing 4s. So remember, a 4 is actually the sort of throw you do when, if I only did 4s, I'd get this pattern. All the throws are from the middle to the outside, but they never cross hands. Every throw here is from a hand back to itself. 2 in one hand and 2 in the other hand. And it was the same if I did them like this. It's the same order. Those are still 4s, even though you might call this a different pattern than this one. Okay? So that's another way to think about an n throw. It's a sort of throw you might do if you were doing n balls and just n balls. So let me make a couple of simplifying assumptions on what sort of juggling I really want to keep track of. And these are called vanilla Siteswaps, with Rocky Road to come later. So vanilla Siteswaps are alternating hands and only one ball in a hand at any time. Okay, so it's easy enough to come up with patterns where that's not true. So here's a perfectly good pattern with 4 balls where I'm throwing 2 throws at the same time. Again, it's 2 in each hand, but it's going to be a little more complicated to notate than if I only have 1 throw to talk about it at a time. So I'm not going to talk about it yet. Another possibility is patterns where you have 2 balls in a hand at once, or not in a hand. There we are. And so 2 balls in a hand at once. Here this is a fairly simple one. Here's a more complicated one. So they're perfectly nice, very interesting patterns that violate these. And we should talk about them, but just not yet. Let's start with these assumptions. So what that means, if I'm alternating hands, therefore, even throws go to the same hand, and odd throws cross. Right? If I'm going throw, 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 then I do a 3 and it comes down 1, 2, 3 later. It'll come down 3 throws later. It'll be in the opposite hand. But this 4, 1, 2, 3, 4, it's the fourth one to come down. Have alternated to come down back in the same hand. So we saw that in the 4, 4, 1. We had the 4, 4, 1. So in 3, everything is crossing, but the 4s and the 4, 4, 1 weren't crossing. Okay, so I wanted to say what are some basic throws you might talk about. Let's not admit the existence of that one yet. So this you've seen the usual cascade. And here, 2 in each hand. What do 5s look like? They're the throws you have when if you're just doing 5. So this again, this would be el ocho con cinco. Every ball is in this figure 8 pattern. So any single ball is in this figure 8, but there are just more of them doing it than there were before. What do 6s look like? So 5, that's, again, it's the cascade, 5-ball cascade. What do 6s look like? They look like 3 in each hand. So that's like that, right? What do 7s look like? What do 10s look like? I'm sure you can imagine it at this point. What do 2s look like? Well, they're the lowest throws you could imagine doing, and they're going back to the same hand because 2 is an even number. So let me now tell you about a bunch of patterns so we can see some examples. So we already saw 3 and 4 and 4-4-1 and 4-4-1-3. Let me show you 5-1, 5-3-1, 5-3-1-3, and then we'll think about how in general to take a pattern and figure out what to take a list of numbers and figure out what the actual juggling looks like. So, okay, remember the difference between these. This is odd length, 4-4-1, and so it was this left-right symmetrical pattern. 4-4-1, 4-4-1, 4-4-1, 4-4-1, because it's odd length, and so sometimes it starts in my right hand, sometimes it starts in my left hand. Whereas 4-4-1-3 is even length, so it's always going to be 4-4-1-3, 4-4-1-3, 4-4-1-3. It's this asymmetrical pattern because it's always starting in my right hand. Okay. 5-1, asymmetrical pattern. It's going to be all 5s from my right hand, all 1s from my left hand. So my left hand thinks that it's in this pattern, whereas my right hand thinks that it's doing 5. And put together, it's this 3-ball shower. All these things that end up with the water terminology, the cascade, the fountain, 2 in each hand is called the 4-ball fountain, 3 in each hand is called the 6-ball fountain. But this one, this way you might try to learn to juggle if you didn't have somebody around to tell you don't, because this is so much easier, that's the 3-ball shower. Another one like that I might mention is 7-1. So 7-1 is the 4-ball shower. And there's also 9-1 and 11-1, but you can guess what those look like. So 5-3-1 is an odd length pattern. I'm just going to do it once in the middle of 3. Out of my right hand will come a 5, and then my left hand will just do another 3, and my right hand will do another 1. So it'll be a 5 and a 1. 5, oops. 5-3-1. 5-3-1. So you see the 1 underneath? Hear it at least. Okay. If I kept doing that, this is an odd length pattern, I will end up with 5s coming from each side. Oops. 5-3-1-3, an even length pattern, the 5s are always going to come from the right, or supposedly the left, but I'm right-handed, and so they come from the right. 7-1 you saw. All right. Let's look at how to, I guess, this kind of hide. Okay. Let's look at how to take a sequence of numbers and try and figure out what's actually going on for a juggler. So here's a sequence of numbers. And when I say 6-6-1-5-1-5, you should think, oh, he means 6-6-1-5-1-5, 6-6-1-5-1-5, and in the infinite past, 6-6-1-5-1-5. So I'm just going to list one cycle of it, and you have to interpret that as a periodic thing. Okay, I'm going to throw a ball at the very beginning, this 6. So that's this 3 in one hand throw that comes back to the same hand. And that's going to come down 1, 2, 3, 4, 5, 6 steps later. But because I'm only drawing this with one cycle, instead of drawing this, I'm instead going to draw that. Okay? And then this 6 would come down on that 6 steps later. But back in the cycle, it's here. 1's okay. The 5 is going to come down 1, 2, 3, 4, 5 steps later on the 1. And the 1 is going to come down here, and the 5 is going to come down 1, 2, 3, 4, 5 steps later back on the 1. So let me make these different colors, actually. There will be that 6 and this 6 and this 1 followed by 5 and this 1 followed by 5. So you should expect to see, so the 6, 6 is going to look like that. Those are what the two balls going way up high and not crossing are going to look like. The 1, 5, 1, 5, each of those is a ball that's going 1, 5, 1, 5, 1, 5, and that's all that ball is going to do forever. Okay. So on the outside, we've got the 6, 6, and in the middle, we have the two 1, 5s chasing each other. 6, 6, 1, 5, 5, 6, 6, 1, 5, 1, 5, 6, 6, 1, 5, 1, 5, 6, 6, 1, 5, 1, 5, 6, 6, 1, 5, 1, 5. All right. Now, how did I know there was only one ball doing these things? In this particular case, there was only one ball. So let me state, in general, how did I know there are only 4 balls here? Let's state and prove a theorem. Theorem. The number of balls is there anybody who has figured out since the beginning of this talk, not who already knew, but who has figured out since the beginning of this talk how to determine the number of balls? I should have stated it as a problem. Yeah?
It looks like that the number of balls per hand is half of the number. For even numbers, and the odd one.
If there's only one number in the pattern, absolutely. But if it's a more complicated pattern, like 5, 3, 1, 3, if there's a bunch of numbers, how many total balls? Well, I'll tell you. Oh yeah?
Is it the number of even numbers plus half the number of odd numbers?
Well, that would be the same for 2, 4, and 6, right? I mean, so it's going to have to actually, it's going to grow as the numbers grow. It's not going to just be how many there are. Yeah?
It's the number of loops you have in that one cycle. So you have 4 loops. And that's
Okay,
6.
but what if my pattern had been 4? Okay, and then you say, oh, that's 1, 2, 3. Then it would look like that. There'd be one loop, but that loop would actually have 4 balls in it, not one ball. So each loop has a certain number of numbers in it. This particular example is silly. It only has 1 ball for each loop. If I had made this a 7, which I'm not going to show you, if I had made this a 7, then there would be 2 guys in this orbit of this juggling pattern. So that's a hint. I increased this number from 1 to 7, and that made it come down in the same place it used to. I increased this from 1 to 7, and which was the length of the pattern, and the number of balls went up by 1. The answer is, it's the average of the numbers of the throws. So 3, 4, 3, 3, 3, 3, 3, 4 for these. This is now 5, and this is 4. Okay, so I'm not going to write out this proof so much in words as give you an example of how it's proved. So the idea is it's easy if all the numbers are equal. If not, find a decrease mn, where m is more than n, and replace with n plus 1, m minus 1. Stir until done. Okay, so let's see an example of this. Let's start with 52512, which is actually a pattern. I could tell you what pattern is it. Well, let me copy it here and we'll see 52512. So it's got the 5 and the 2, and going to the 1, going to the 2, and the 5. So it's got these throws we know, these 5s. It's got these 2s that I told you about. But I'm going to be lazy. I'm not going to do the 2s like this. I'm going to do them like this. And so actually, it's time for me to admit what goes on in a couple of the holes I left there. 2, I'm going to use to denote a hold. So 1, you've seen a bunch of times now, is this handoff. 0, I'm going to use to denote an empty hand. So it's easy to mistake 2 for 0 because in both cases nothing happens. But they're different. Here's the pattern 4-2, 4-2, 4-2, 4-2, 4-2, and the average is 3. And here's the pattern 4-0, 4-0, 4-0, and the average is 2. So, okay, so here's 5-2-5-1-2, and here are the orbits of 5-2-5-1-2. There's a ball that's doing 5, so I'll explain in a moment how to soup this up to tell you how many balls there are in an orbit. There's a ball that's doing 5, there's another ball that's doing 5, and that's all they do forever. So they're like this, they're chasing one another as these 5s. And then there's another ball that's doing 2s and 1s. Here it is. So that's only getting handed off and waiting. So if you want to see this performed with a small baby in place of this green cup, then you should look on YouTube for Knutson and Giocolieri, jugglers in Italian, where I juggled a small child in front of 700 Italians. So this is called the baby juggling pattern for that reason. I've also seen it done with a monkey. I saw it done, I didn't do it. I've also seen it done with a 170-pound man. It was really impressive. He would be hoisted from here to there a couple of times. Okay, so that's the baby juggling pattern, and I want to prove to you that the number of balls in it is 3. So what I'm going to do is look for a decrease. Say, here's this 5 and then this 2, and say, well, instead of throwing these balls so that the 5 comes down then and the 2 comes down then, let's do this little surgery on the pattern and have them swap sites. This is the origin of the name. So that means that instead of the 5 coming down then, it's the 2 that's supposed to come down then, but that, instead of the 5 being thrown from here to come down then, it should wait one step and be thrown from there. So instead of being a 5 to get there, it should be a 4 to get there. That's the m minus 1. And instead of this 2 being thrown from then to get there, it should be thrown from one step earlier, which means it needs to be a 3 to get there. So that's the n plus 1. Okay? So what I've done is I've made a slightly different pattern. It's the numbers are a bit more even, and which you could believe that if I kept doing this, I could get all the numbers to be the same. So the numbers get a little bit more even, and the average doesn't change because the sum doesn't change. And it's still a perfectly valid pattern. I know for sure I don't have 2 balls coming down at the same time because I know who's coming down at what time. They've just swapped sites. So we repeat this. 3, 4, here I've got this decrease. So I can turn that into a 2 and a 4 and a 2. And then I can turn these into, so that was swapping these, and then turn these into 3s. Okay? And when do you get stuck? You only get stuck if there are no decreases. So you might wonder, what if the pattern you get stuck at looks like 2, 3, 3, 3, 4? You say, well, my numbers aren't all the same, but there are no decreases. But that's the same thing, really, as 3, 3, 3, 4, 2. It's the same pattern, just started in a different place. And now there's a decrease. So if there isn't a decrease somewhere, it's because all the numbers are equal. And at that point, we're in the easy case, QED. Okay. I see. Interesting. Does that really not go behind there? Oh, okay, good. All right, let me show you a few more patterns. 5, 2, 5, 1, 2. 5, 6, 1 is my favorite pattern. 7, 2, 7, 2, 7, 1, 2. 5, 0, 1 is a surprisingly good one. 5, 5, 2, 5, 5, 5, 5, 0, 4, 5, 3. Let's see some of these. So let me start with this one, 5, 0, 1. So that's got one orbit. So I should have told you how to generalize this. The number of balls in an orbit is equal to the sum over that orbit divided by the length of the pattern. So if you believe this theorem now, then how do you prove that? Well, you say, I can break this 5, 2, 5, 1, 2. I could break 5, 2, 5, 1, 2 as being this orbit plus this other orbit plus this other orbit. Each of these three orbits, they don't talk to each other. They don't need the other balls to be there. Those other throws could just be zeros. So I've broken this pattern as a sum of three other patterns where each of those patterns only has one orbit and the hands are empty otherwise. Then you apply the previous theorem. Okay, so the total in this orbit is 6. I divide by the length of the pattern 3, and I find that there's 2 balls doing that. And in the other orbit, there's 0 balls. So that is this 2-ball pattern. Each ball here is doing 1s and 5s. So each ball here thinks that it's in a 3-ball shower. Remember, that was this pattern 5, 1. But one of the balls thinks it's in this shower, and the other one thinks it's in this left-handed 3-ball shower. So this 2-ball pattern is much harder than doing 3. This pattern is almost as hard as doing 5. It's one of the ones that I teach people if they already know 3, they already know 4, and they want to learn 5. This is a good thing to practice. And you saw it before. You saw it with this other ball in it. If I take the purple ball out of here, can I do that? You'd think I should be able to. If I take the purple ball out, then I get the 5, 0, 1 instead of the 5, 3, 1 I was doing before. Okay, I wanted to show you the difference between zeros and 2s. These are 2 different ways to think about 4 out of 5. So if I'm juggling 5 balls, and I drop one, I drop one, and I drop one, there are 2 ways that I might go into doing 4 out of 5 and trying to hide that fact. Dropping 2, it's harder to hide that fact. One is I could always throw, and when I eat, I can throw even if there isn't a ball coming to my hand. Ooh, sorry. So this is 5, 5, 5, 5, 0. I have this empty hand there. And it's much more difficult than 5, 5, 2. And the 5, 5, 2, whenever I don't have a ball coming to a hand, I don't throw. I only throw if I have to avoid collisions. So the rhythm you hear is, whoops, I did a 0 there. the rhythm you hear is this, sounds like 2 throws, but it's 2 out of 3. It's 5-5-2, 5-5-2, 5-5-2. I could show you the full hands there. 2, 2, oh dear. 2, 2, 2, 2, 2. Instead of the empty hands that I had with 5-5-5-0, 5-5-5-5-0. So that's the difference between 2s and 0s. 5-6-1, so that's like 5-0-1 and like 5-3-1. It's got the same orbit structure, but instead of having no balls in the middle, or having 1 ball in the middle, like I had in 5-3-1 that I showed you before, it's always doing 3s, I'm going to have 2 balls, and they'll be doing 6s. So they'll be on the outside doing these 6s. Like I had in 6-6-1-5-1-5 from before, that guy, but the order's slightly different. So there's going to be 2 balls in the middle doing the 5-0-1 you've seen, and 2 balls on the outside doing 6s. So that's my single favorite pattern. 7-2-7-2-7-1-2. That's got these 3. That's length 7. So I've got 3 balls that are always doing 7s, and here I have the baby. So this is a baby juggling pattern with 3 balls and a baby instead of 2 balls and a baby. Oh, sorry, baby. This I did not perform for the Italians with a baby. Yeah. 4-5-3. Should I really have written that one there? So 4-5-3. It's a very beautiful pattern. It's got 4, and you know what that looks like, 2 in each hand, or what it looked like 10 minutes ago, 2 in each hand. And it's got 5 and 3. So maybe I should just show you 5-3 first. So that's like 5-1 that we saw before, where my right hand is doing something harder than my left hand, except my left hand isn't just doing these handoffs now, it's doing 3s, these little 3s. So my right hand's doing all 5s, and my left hand's doing all 3s. And we get this sort of Star Trek insignia picture. Okay, that's called a half shower. I told you this one's called a full shower. So 4-5-3, I'm going to do that in the middle of 4. I'll be in the middle of 4, and I will have a 5 and a 3 in there. So there's the 5-3. So that's doing it just once in the middle of 4. And so one thing that's clear with the numbers, you could think of it, oh, there's 4s and there's the 5-3, so it's related 4 and it's related 5-3. Or you could think I could knock this 4 down by the length of the pattern to get 1 and say it's like 1-5-3 that we've already seen. So with the numbers, it's really very easy to start seeing relations between patterns, which is part of the point of having this numbering system. So 5-3-4, the other thing you could do with it, of course, is look at the orbit structure and see that the 3 is its own orbit. That's the silver ball that's in its own orbit. The other 3 balls, though, are all 5, 3, there. The other 3 balls are all in the same orbit, though. So it's much harder to figure out what they're doing. Each one of them is doing a 4, then a 5, then a 4, then a 5, then a 4, then a 5. It's only the ball that's in the 3 orbit in this 5-3-4 pattern that is doing something simple. Oops, there we are, approximately. All right. Yeah.
So is there a way to estimate from the numbers how complex, how difficult is a certain pattern to do? Let's say that we fix the average, then what's the best way to estimate how complicated it is?
So the question is, how hard is it to how do you look at a pattern and figure out how hard it's going to be from the numbers? Well, so a number of things come into it. One is the highest throw is really the most obvious thing. More than the average, really the highest throw is going to be the single biggest determiner of the difficulty. And it may well be that, like me, you might be very right-handed and much better at putting a high throw out of your right hand than out of your left hand. And so you could look at a pattern and say, well, 7-1, that only has sevens from the right hand, not from the left. 7-7-1 has sevens out of both hands, and so it might be much more difficult. Another thing is if you have a high throw and a low throw, like a 7 and a 3, then you can't see them. And so that's sort of hard to capture from a mathematical theory, but it's really clear from the juggler point of view how difficult that's going to be if you're mixing those heights. So it's not as simple as saying, oh, I don't want the throws all to be roughly the same so I can see them, because zeros, ones, and twos you don't have to look at. It's only once you get to a 3 you have to look at it. So I mean, you're very much asking an applied mathematics question here, and so it doesn't have a very simple and clear mathematical answer. Any other questions at this point? Yeah.
Yeah, how can you determine what the rhythm is going to sound like? Can you do that just by looking at the numbers and be like, bang, know what the rhythm is?
Well, the single biggest determiner is whether it's going to be, whether it's odd length or even length. And that an odd length 1 is going to sound more even. But the other thing is just certain throws are noisier than other throws. Namely, 1s are noisier than other throws. And 0s and 2s don't make any noise at all. So that's really, I think, the most of it. Yep.
Do you keep the balls on the same plane when you do it in the same orbit?
Pretty much I keep them all in the same plane, and that's very much by choice. I mean, when I see people, when you see people who are learning 2 in one hand, for example, and they're doing this, where they're throwing them back at themselves, that really doesn't extend if you want to start doing anything harder. It's much harder to avoid collisions by depth perception. So absolutely, if you want a clean, smooth pattern where you can see what's going on, keeping them in the same plane works a lot better. Okay. Yep.
Did you create the number code, or is that just how
No.
you learned juggling?
No. So it was created by 3 different groups of people working independently in 1985. And so I'm sure, I could easily believe it got created by a number of people before then, and they didn't tell anyone. And I certainly know it's been recreated by a bunch of people since then, before it really got popularized. But basically, we give credit to a couple of guys in California and this one group in Cambridge for creating it. It's very non-standard, or I mean, more and more so as time goes on. 1985 is a long time in the past now. It used to be very non-standard for people to learn this as part of learning to juggle. I mean, this is really, most of the things I'm showing you are so much harder than doing 3. They're only going to be appreciated by somewhat advanced jugglers, and most of them are not at all what you'd want to work on if you were juggling for money. I go to juggling conventions, and about half the people who come to them are professionals. Street performers, cruise ship jugglers, and they'll do this for fun in their spare time. But absolutely, it has nothing to do with their work. Yeah.
How does juggling for money differ?
That you want to do showy things. So, like when I'm juggling clubs, for example, and I'll want to be working on clubs in a way like, say I'm juggling clubs with somebody else. I like to have throws that are pretty high and lofty and go slowly, and such that things are as easy as possible. Whereas if you want to do that for a paying audience, then you want to throw it really fast, so the whole thing looks really, really hard. I mean, that's just a basic thing, And there's going to be a lot of this sort of stuff. I mean, there's just a lot of things that, are very orthogonal to this as a, intellectual pursuit. Yeah.
You mentioned juggling with other people. How do you extend your notation here? You have 2 or more teams.
Let me get to that when I talk about even juggling with oneself and having two hands. All the stuff I've been telling you secretly has been one-handed juggling. Mathematically, this is all really just the same as talking about one-handed juggling. So I'll get to that. Yeah?
I wanted to know if there are clearly some patterns which cannot be realized with alternating hands because you have two balls falling on the same hand at the same time.
Again, so you're getting beyond vanilla Siteswap now. It's the same issue, I'd say.
Yeah, I just wanted to ask if there is an easy to check condition such that a list of numbers gives you a doable pattern.
Oh, right. So that's an issue. Yes. So the basic point, of course, is that you shouldn't have two balls landing at the same time. If my pattern has 4 and 3 in it, then I shouldn't have 4 and 3, right? So that's no good. No, it's that if I had, say, a 5 and then 3 steps later I had a 2. So you don't want to have a distance d between things and have a throw and have another throw where these guys are both coming down at the same time. So you have to make sure there are no collisions of this sort. You have to look through the numbers and look at every pair and see that there aren't going to be collisions. And that guarantees you half of what you want. You want, for the pattern to be juggleable, you want that there are never two balls landing at the same time. And the other is you actually want a ball landing. You don't want to say, okay, I'm trying to make a 5 now, but I don't have a ball. So, but pigeonhole principle says, if you have this finite periodic pattern and no two balls land at the same time, then balls land at every time. So there will be a ball. So the only thing you have to check is one direction.
It seems a non-polynomial problem because you really need to check, I don't know, a lot of conditions.
Well, I said you have to check every pair. So it's quadratic in the length of the pattern. Okay. So, I guess we don't need that stuff anymore. Let me tell you about, I guess I want to get to now, about how to generalize this if you want to deal with multiple throws at the same time, and or you want to deal with multiple hands throwing at the same time. So a multiplex is when you have many balls in the hand, in one hand at the same time. So let me give it a basic example. I'm doing 3, and at some point I catch a second ball. Oh, maybe that was too simple. I'm doing 4. At some point I catch a second ball. Oh, yeah. Which example did I want? I'll jump straight to this example. So in this one, what's going on? Well, it's a symmetrical pattern, so that means it's odd length. If you listen for a little while, you'll figure out that that length is 3. You'll notice that I have a ball in a hand, and I put another ball in there. So that means that this ball is waiting, and another ball is going into there. So I'm waiting with one hand, and then I'm handing off another ball into there. And now I have 2 throws to do. And the way I'm going to denote that is I'll put brackets around it to say that these 2 throws are happening at the same time. So what are those 2 throws? Let's see. I want, what are those 2 throws in this pattern? So they look like that. So there's a low one and a high one, and it's the high one that is crossing. So there's an even number and a larger odd number. And what they are, it turns out, is 4 and 5. Okay. So this is how I'm going to denote a multiplex pattern, where I've got several balls I want to throw at a given time. And now, what do you still need to check? You need to check not that at any given time there's only one ball coming in. You need to check that at any given time there's the right number of balls coming in. So when I get to this point, I don't want to look down and say my hand is empty or my hand is one ball. I want to know that I have 2 balls coming in, and I do. So I'm going to draw the same orbit picture for this pattern as I was doing for non-multiplex patterns. At this time, I throw the 4, and it's going to come down 1, 2, 3, 4 steps later. And I throw the 5, which will come down 1, 2, 3, 4, 5 steps later. And here, that's good. I have 1 ball coming in, 1 ball coming out, 1 ball coming in, 1 ball coming out, 2 balls coming in, 2 balls coming out. So this is a valid multiplex pattern. I showed you a simpler one before where I had just doubled one of the balls. So instead of having 1 green, 1 red, 1 silver, I've doubled the silver ball. So what's that pattern? That's 3, 3, and then I doubled that one. And the orbit structure is very simple. So that's one of the things you need to generalize beyond vanilla Siteswap. And the other is synchronous throws. So at this point, I want to say at any given time, not the throw that I'm doing, but the throw that I'm doing for my right hand and the throw that I'm doing for my left hand. And so this is the standard notation for it among jugglers that will use parentheses, not brackets. And you can mix these two. You can have synchronous patterns that are also multiplex, so that inside here, seeing what your left hand is doing, you might have several throws going on. So let's say I have, and let me say here, there's a convention which is to use all even numbers. So let's say I have this pattern called 4, 4. So that means I'm going to be repeating that forever. So 4, 4, then 4, 4, then 4, 4. Okay. Now, if I had, just like I was repeating 6, 6, 1, 5, 1, 5 here, if I were using the same rule as I was here of, okay, you take an arrow out of a number, count that many numbers forward. That's where the arrow is pointing. So the 5 is pointing 1, 2, 3, 4, 5 steps forward. Then you might think these 4s are going to be pointing 1, 2, 3, 4 steps forward. But the convention is that there's nothing here. You count the gap in between. So this is actually going pointing 1, 2, 3, 4 steps forward. And this one also. So why do we do this? Because this pattern as drawn is this one. And it seems silly to call those 2s, even though mathematically it would make more sense to call these 2s. They're landing 2 steps in the future. But since that pattern's so much like this one, we would prefer to call them 4s. So we make that choice, that we take what's the natural thing to do mathematically and double all the numbers, so that you don't have to say, well, he said 4. But is that 4 like this sort of 4, or is that 4 like this sort of 4 because he's doing something synchronous? So it's just a choice of mathematical convention.
It's a choice with respect to the average theorem that you stated.
And it does that. So that is a good motivation to make this choice. That again, the average of the numbers will be the number of balls. Yeah.
In that 3, 3, 3, 3 that you just proved, the average there is 3, but you have 4 balls.
How does the averaging theorem generalize? You have to add up all the numbers and divide by the length. Not by the number of throws, by the length of the pattern. So before, the length of the pattern, the number of throws was the same. But now the number of throws is there are 4 total throws here, I guess. And the number of numbers is 4, and the length of the pattern is 3. So the total here is 3 plus 3 plus 3 plus 3 divided by 3 is 4, like it's supposed to be. So I forget when we started. I have one more topic I could include, but it'll be about another 5-10 minutes. Yeah.
Do you want to stop and have questions, or do you want to hear one more topic?
Which is the topic?
I'm afraid it's really cool. All right. So here's another way to think about what these numbers mean and how you might talk about a juggling pattern. Let's say we are watching a juggler on videotape, and we stop the videotape and ask, how much information do we have about the future? We don't know what throws the juggler is going to make in the future, but we do know what throws the juggler has made in the past. So we know how many balls there are in the air and when those balls are going to land. So another way to say that is imagine that somebody's juggling and they stop. What does it sound like? Well, in this case, if I stop just after I make this left throw, you hear catch here, pause, catch here. So let me draw that as catch, catch, pause, catch. And I might say, so in the past, I've always caught balls. And in the future, I've got no more balls that are going to land. So here's now. And the balls that I have in the air, they're going to land at those 3 times. So here's where the action is, of course. I know in the past, I always caught a ball. And there's only 3 balls in the air. So let me just write this as the state of the, so this is a juggling state. Okay, so what was I doing in that pattern? Which pattern is this? Yeah, what are the numbers? 5, 1, yes. There's 5s from my right hand, 1s from my left hand, average of 3. Okay, so now I'm going to do a 5. This was just after I did the 1, and you heard the 1 land here. So now I'm going to do a 5. And what's going to happen? I've got a ball in my hand right now, and I'm going to throw it so it will land. So the time will move forward 1 step. I'll throw this ball so it'll land 1, 2, 3, 4, 5 steps in the future. I'll still have this and this, but instead of that, I'll get an X there. That this ball has been thrown to land 5 steps in the future. Okay, what did I do after that? So this was my right hand 5, now I do my left hand 1. The ball's in my hand, I'm going to throw it to land 1 step in the future. Time will march forward and I'll get XX dash X. That's back here. Okay. So what if I were doing not this complicated thing, but I were doing the 3-ball cascade? That's this state, where I just stop juggling in the usual 3-ball cascade, and you hear catch, catch, catch. No pauses. So from here, I could throw the ball I'm catching right now, and it'll land 1, 2, 3 steps later, and I'll get X, X, X again. That looks like that. How can I relate these? What if I'm doing the 3-ball cascade, and I want to go into the 3-ball shower? That's what this is for. It's for figuring out these transitions between patterns. So you look at this and say, I want to get from this state to that state. I'm going to need to create a hole. So instead of throwing a 3 to land then, I will throw it to land 1 step later and make a hole there. That will be this hole. So I'll throw a 4. Okay, what does that look like? I'm in the middle of 3. I want to get to 5s from my right hand. And so I want to do this just before I do the 5 from my right hand, and you do the 4 from my left hand. That's this thing, this 2-in-1 hand throw. So I'm going to do that. I'm going to use the green one for that. There will be this green 4, and we'll see what color follows it. There. And it was followed by that 5 up above. Let's see that again. So the next time, green 4, 5. Oops, I did the 1, which I wanted 2. Okay, one more time. Green 4, 5, 1, 5, 1, 5, 1, 5, 1. Okay. What if I want to get back from the cascade, from the shower to the cascade? So I could, at this point, throw the ball that I'm holding as a 2, or I mean hold it as a 2. So that's this 2. And so that means I'll be doing 5, 1, 5, 1, 5, 1. And instead of doing the 5, I do a 2, and I'm back at 3. Okay, so 4 to get in, and 2 to get out. Okay, 4, 5, 1, 2. Now 2s are boring. So what could we do instead that would be more interesting to look at? Instead of doing this 2, we can't do a 3. We'd cause a collision. We could do a 4. And if we do a 4, we get to this guy will now land. After that, I'll get x dash x and another x. Okay? And at this point, we could fill in a 1. So I'm in 3, and I go 4, 5, 1, 5, 1, 5, 1. Now, instead of doing a 5 out of my right hand, those high crossing ones, I'm going to do a 4 out of my right hand. There it is. And I'm back at 3. So 4 to get in, and right hand 4 to get out. Left 4 to get in. Oops, I'll do it all with the red ball. So there'll be the left 4 to get in, and right 4 to get out. Here it is. Oh, no, not that time. Right 4 to get out. There we are. Okay. And note, here's 4, 4, 1. You saw that one before. Here's 4, 4, 1, 3, 4, 4, 1, 3, 4, 4, 1, 3. You saw that one before. Where's 5, 2, 5, 1, 2? Well, we'd start here, and we'd do 5. And we'd do 2. That'll take me to there. And then we do 5, 1, 2. 5, 2, 5, 1, 2. So a juggling pattern is the same as a closed loop in this directed graph of juggling states. And so you can ask questions then like, what does a juggling pattern look like if it doesn't repeat a state? If it repeats a state, that means you can break it up as 2 juggling patterns put together. And you get these impossible combinatorial problems. A very interesting one, though, is what does random juggling look like? You could say, I want to have only n balls and, or let's say b balls, length n pattern. Then I'm going to get only finitely many juggling states, n choose b, many juggling states. And I could just do a random walk on there. At any point, I do one of the throws available to me, unless my hand is empty, and then I have to do a 0. So that has been analyzed, this random juggling, the stationary state of it. So the likelihood you'll find yourself in a given juggling state, if you're juggling randomly, has been calculated in this paper called Juggling Probabilities in the American Mathematical Monthly. So this is the part of things that I was personally involved in the theoretical, coming up with this picture of juggling states to describe juggling patterns, and it's really handy for coming up with how to get from one trick to another. So, and I'll stop there.
Thank you very much, Allen. This was very nice. This is part of our Math Awareness Month celebration. The Math Awareness Month is a national event. Each year it has a theme. This year is mathematics and sports, and we're declaring juggling a sport. Here's your certificate of appreciation.
Thank you.
Another means by which we celebrate Math Awareness Month is by having a t-shirt design contest with high schoolers at Ithaca High School. The students design t-shirts in recognition of the theme for Math Awareness Month each year. And then people at Ithaca High School vote on the t-shirt design, send their favorite designs here, and then we vote, put all of that together, and come up with a winner. And this is this year's winning design. So I'd like to present you with a Math Awareness Month t-shirt.
Thank you.